Hello, calm souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you were here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else we need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. Now, let's gently explore something many of us have felt, even if we've never named it. There is a kind of silence that belongs only to deep space, not the silence of an empty room, or the hush that falls after a storm. This is something older, something without edges. It is the silence of distances so vast that light itself takes millions of years to cross them. It is the silence between galaxies, between those pale, luminous islands of matter drifting through a darkness that has no shore. If you could stand somewhere outside time and simply watch, you would see them, galaxies turning slowly, unhurried, like embers cooling after a fire that burned before there was anyone to name it. Spirals of 100 billion stars, elliptical clouds of ancient light, thread-like filaments connecting one cluster to the next, forming patterns so large that the human mind cannot quite hold them whole. And all of it, every star, every nebula, every cold rock orbiting at the edge of some quiet solar system, all of it is made of matter, the same fundamental stuff, arranged in different ways, shaped by different forces, at different scales and temperatures, from the largest galaxy to the smallest grain of interstellar dust. The universe is built from common ingredients, and those ingredients, those deepest units of structure, obey the same rules whether they are here or a billion light years away. Let us descend, then, slowly, from those drifting galaxies, toward something closer, a single star, perhaps, one among many in a spiral arm, circled by planets. On one of those planets, there is an ocean, and in that ocean, water, and in that water, molecules, and in those molecules, atoms. We are entering a different kind of space now. The distances are smaller, but they remain vast in their own way. An atom is mostly emptiness, a nucleus at its center so small that if the atom were the size of a cathedral, the nucleus would be a grain of sand at the altar. Around that grain, electron clouds drift and shift, forming the chemistry that makes water, and salt, and stone, and the carbon backbone of every living thing. But let us go deeper still, past the electrons, past the outer regions of the atom, down into the nucleus itself, that tiny, dense heart, where nearly all the mass of the atom is concentrated. Inside the nucleus, there are protons and neutrons, bound together into an almost impossibly tight arrangement. And here is where something interesting, and quiet, and remarkable begins to reveal itself. Because these protons carry electrical charge. They are all positively charged, and according to the laws of electromagnetism, like charges repel, two positive charges placed near each other will push apart with a force that grows stronger, the closer they come together. Yet inside the nucleus, protons exist in extraordinarily close proximity. They are packed together at distances so small that their electrical repulsion should be immense, far stronger than anything gravity or electromagnetism could counter. If only electricity and gravity were at work, every nucleus larger than hydrogen would simply fly apart. Matter as we know it could not exist. Atoms would not form. Stars would not burn. There would be no planets, no oceans, no living things looking up at the sky with quiet wonder. And yet, here we are. The nucleus holds together. Protons and neutrons remain bound. Despite everything that should pull them apart, the atoms of the universe do not dissolve. Matter is stable, enduring, present, something else must be at work, some other force, one that operates only at very short distances, one that is powerful enough to overcome that electrical repulsion, one that is simply not visible at the scales we ordinarily inhabit. Physicists call it the strong nuclear force, and the particles that carry that force, the silent messengers that travel between quarks, and bind protons, and hold the nuclei of every atom in the universe together. Those particles are called gluons. You have never seen a gluon. You never will. Not directly. They are confined to a world far smaller than anything any microscope has ever resolved. They do not exist in isolation, in the way that electrons or photons do. They live and work in an inner architecture of matter that is almost entirely hidden from ordinary experience. And yet, everything you see, everything you touch, everything that has weight and takes up space, all of it rests upon their work. This is a journey toward that hidden world, not a dramatic descent, not an adventure into exotic realms, just a slow, careful passage inward, toward the place where matter finds its structure, and the universe holds itself together through forces we are only beginning to understand. We begin at the surface of things, as science always does, and we descend from there. For most of human history, the question of what matter was made of remained philosophical, rather than scientific. Atoms were an idea. Long before they were a measurement, the ancient Greeks imagined indivisible units of substance, but they had no tools to find them. Centuries passed, theories came and went, and then, slowly, over the course of the 19th and early 20th centuries, something changed. Experiments began to reveal structure where none had been suspected. The discovery of the electron, near the end of the 19th century, was a turning point. Here was something smaller than an atom, a constituent, a piece. Atoms were not, after all, the indivisible limit of matter. They had parts, and if they had parts, those parts could be studied, and the rules governing their behavior could be explored. With the discovery of the nucleus came a new puzzle. Ernest Rutherford and his collaborators, in the early years of the 20th century, directed beams of charged particles at thin sheets of metal and found that most passed straight through, confirming the mostly empty nature of the atom. But a small fraction bounced back sharply, indicating a dense, concentrated center. The nucleus was real. It was small, and it was heavy. Then came another realization. If the nucleus contained protons, positively charged, how did it hold together? The electromagnetic force was well understood by then. James Clerk Maxwell's equations described it precisely, and those equations made clear that protons, packed together at nuclear distances, should experience repulsive forces of enormous magnitude. A nucleus of 2 or more protons should instantly fly apart. But it did not. Physicists of that era faced a genuine mystery. The stability of matter itself was unexplained. Something was holding protons together, something strong enough to overcome electromagnetic repulsion at very short ranges, something that had no apparent analog. In classical physics, this gap in understanding was not a small one. It was not a footnote or a minor anomaly. It was a fundamental hole in the picture of reality. Without an explanation for nuclear binding, physics could not claim to describe matter at its deepest accessible level. For a time, the approach was phenomenological. That is, physicists described the effect of nuclear binding without fully understanding its cause. In the 1930s, the Japanese physicist Hideki Yukawa proposed that the force holding nuclei together was transmitted by a particle, a mediator, a messenger. He called it the meson. Hideki Yukawa's idea was elegant. Just as photons carry the electromagnetic force between charged particles, some analogous particle must carry the nuclear force between protons and neutrons. The prediction was made before the particle was found, when cosmic ray experiments eventually revealed particles of roughly the predicted mass, there was cautious excitement. Something was being seen. Something was answering the question Hideki Yukawa had posed. But as accelerators improved, and as experimenters began probing higher and higher energies, the picture became more complicated. Rather than simpler, more particles appeared, not just protons and neutrons and Yukawa's mesons, but a growing collection of short-lived, energetic particles that seemed to have no obvious place in any tidy taxonomy. This era, roughly the 1950s and into the 1960s, produced what some physicists described with a kind of bemused exhaustion as a particle zoo. There were too many particles for each of them to be truly fundamental. The pattern was familiar from chemistry. When you find too many elements arranged without apparent logic, there is usually a deeper structure waiting to be discovered. The periodic table eventually revealed the underlying architecture of atomic structure, the rules of electrons, protons, and shells. Something analogous was surely waiting to organize the particle zoo. In the early 1960s, Murray Gell-Mann, and independently, Yuval Ne'eman, noticed that many of the observed particles could be organized into geometric patterns, groups related by certain symmetries. The patterns were not accidental. They reflected something real about the underlying structure of matter. Murray Gell-Mann proposed a name for that structure: quarks, subcomponents, entities more fundamental than protons and neutrons, from which the observed particle spectrum could be assembled. The idea was radical. At first, it seemed almost too abstract, but the mathematics was compelling, and the patterns it predicted matched what was being observed. Quarks, however, came with a peculiarity. They had never been seen in isolation, despite extensive searches. No experiment had ever found a free quark, a single isolated constituent of a proton. They seemed always to remain locked inside larger composite particles, never escaping. This was puzzling. It suggested that the force binding quarks together was unlike any force previously encountered, one that grew, rather than diminished, as quarks were pulled apart, a force that seemed to forbid isolation. Understanding that force, its mediators, and its rules became one of the central projects of theoretical and experimental physics in the second half of the 20th century. From that effort eventually emerged quantum chromodynamics, a theory of remarkable precision and depth, describing how quarks interact through the exchange of particles that carry a force, both familiar in structure and utterly unlike anything in ordinary experience. Those particles, the carriers of that force, are gluons. The name is direct, almost blunt. They glue quarks together. They are the messengers of the strong force at its most fundamental level. And to understand them, we first need to go inside the proton itself, into that tiny, dense world where quarks move and interact and exchange these invisible messengers. In a constant, quiet storm of activity, there is a tendency, when first learning about atomic structure, to imagine the proton as a small solid sphere, a billiard ball perhaps, round and definite and opaque, sitting at the center of the nucleus, like a red bead on a wire. This image is understandable. It is how protons are often drawn in textbooks for younger students. It is a useful fiction for the purposes of basic chemistry, but it is not accurate, not at the level we are now exploring. A proton is not solid. It has no definite surface, no fixed interior. It is something far stranger and more dynamic, a structure that exists as much in terms of fields and probabilities as it does in terms of particles and positions. When physicists examine the proton at high resolution, using the tools of particle physics, which we will come to later, what they find is not stillness, but constant motion, not simplicity, but extraordinary complexity. Inside the proton, at any given moment, there are quarks, 3 of them. In a sense, though even this statement comes with important qualifications, the proton contains 2 quarks of one type and 1 of another. The type that appears twice is called the up quark. The type that appears once is called the down quark. 2 up quarks and 1 down quark bound together in a configuration that gives the proton its properties, its charge, its mass, its stability. But the language of contains is a little misleading because the quarks inside a proton are not simply sitting still inside a fixed container. They are in motion, they interact, they exchange energy, and they exchange that energy through gluons, messenger particles, constantly passing between them, carrying the strong force that keeps them bound. A more accurate image, if images are possible here, might be something like this. Imagine a small space in which 3 points of concentrated energy are connected by a web of invisible threads that are themselves in constant motion. The threads are not passive. They carry energy. They pull. They vibrate. They fluctuate. And sometimes, from the energy contained in those threads, new particle-antiparticle pairs briefly appear and vanish, there, and then gone, like ripples on a pond, that form and dissolve before they reach the shore. Physicists refer to the quarks that define the proton's identity, the 2 up quarks and the 1 down quark, as valence quarks. But in addition to these, at any given moment, the proton contains a fluctuating, shifting population of what are called C quarks, pairs of quarks and antiquarks that arise briefly from the energy of the gluon field before annihilating and vanishing again. This sea of virtual particles is not hypothetical decoration. It has real consequences for the proton's behavior and properties. The down quark has a slightly different mass and charge than the up quark. Together, their properties determine much about the proton. The up quark carries an electric charge of positive 2/3, while the down quark carries a charge of negative 1/3. 2 up quarks and 1 down quark therefore give the proton a total charge of 2/3 plus 2/3 minus 1/3, which equals positive 1. The proton's charge, that familiar unit we encounter in chemistry and electromagnetism, is the sum of its constituent quark charges. The neutron follows the same logic. A neutron contains 1 up quark and 2 down quarks. Its total charge is 2/3 minus 1/3 minus 1/3, which equals 0. The neutron is electrically neutral, and this difference in quark composition between proton and neutron, despite those particles being so similar in many respects, is what distinguishes them. The up quark and down quark are the lightest of the 6 types, or flavors, as physicists call them, of quark. The others are considerably heavier and do not appear in ordinary matter in any stable configuration. They arise briefly in high-energy collisions before decaying rapidly into lighter particles. But up and down quarks, bound together by gluons, form the protons and neutrons that constitute the nuclei of virtually all the matter we encounter in the ordinary universe. The masses of the quarks themselves are small, surprisingly small. The up quark and down quark together, if their masses were simply added, would account for only a tiny fraction of the proton's measured mass. The rest, the vast majority of what we measure when we measure a proton, comes not from the quarks themselves, but from the energy of the gluon fields and the kinetic energy of the quarks moving within that field. This is a remarkable fact, and one we will return to in more depth. It means that most of the mass of ordinary matter, including the mass of every proton and neutron in your body, in the stones beneath your feet, in the iron, at the Earth's core, is not the mass of any individual particle, but the mass of energy itself, converted according to the deep equivalence that Albert Einstein described. Matter is, at this level, predominantly a form of bound energy. The gluon field is not just a structural feature of the proton, it is the proton, in a very real sense. The quarks are concentrations. Within it, the mass is carried by it. But to understand how gluons do this, we need to understand what gluons are. In the language of modern physics, forces are not simply invisible pushes and pulls. They are, at the quantum level, the result of particles exchanging other particles. This is one of the most consequential ideas in 20th century physics. The notion that what we experience as a force is, at the microscopic level, a constant process of messenger exchange. Consider the electromagnetic force, which is the most familiar of the fundamental forces to everyday experience. When two electrons repel each other, or when a proton attracts an electron, what is actually happening? According to quantum electrodynamics, the theory that describes electromagnetism at the quantum level is an exchange of photons, not the photons you see when you look at a lamp, but virtual photons, fleeting, ephemeral excitations of the electromagnetic field that carry momentum and energy from one particle to another before vanishing back into the quantum vacuum. Photons are the force carriers of electromagnetism. They are, in the language of the field, gauge bosons, particles defined by their role in mediating a force. Gluons are the gauge bosons of the strong nuclear force. They are the particles that quarks exchange, and through that exchange, they exert the force that keeps quarks bound together inside protons and neutrons, and by extension, keeps protons and neutrons bound together inside atomic nuclei. Like photons, gluons are massless. They travel at the speed of light, and like photons, they are bosons, particles with integer spin, which means they do not obey the exclusion principle that governs fermions. Like quarks and electrons, multiple gluons can occupy the same quantum state simultaneously, which has important consequences for how gluon fields behave. But here is where gluons diverge sharply from photons and from anything with a clear everyday analog. Photons are electrically neutral. When a photon carries the electromagnetic force, it does not itself carry electric charge. It is a neutral messenger. When it is exchanged between two charged particles, the charges of those particles are not altered by the exchange. The photon simply transmits the force. Gluons are not neutral. They carry what physicists call color charge, and this changes everything about how the strong force works. Color charge is one of those concepts in physics that requires a careful introduction, because the word immediately suggests something visual, something to do with wavelengths of light and what our eyes detect. But in particle physics, color has nothing to do with any of that. It is a label, a technical term, borrowed and repurposed from ordinary language for a property of quarks and gluons that has no equivalent in everyday experience. It is, if you like, a kind of charge for the strong force, analogous to electric charge for electromagnetism, but with a richer internal structure. Quarks carry color charge, gluons carry color charge, and the interactions between them, the exchanges of gluons, the absorption and emission of color charge, are governed by a beautiful and precise mathematical theory called Quantum Chromodynamics, or QCD. The word chromodynamics is itself constructed from the Greek word for color, chroma, because the theory describes the dynamics of color charge. It is, in essence, the physics of color, not visible color, but the abstract, symbolic color that defines how quarks and gluons interact. When a quark emits a gluon, something important happens. The quark's color charge changes. The gluon carries both the color the quark had and an anticolor, the complement of what the quark is absorbing. When another quark absorbs that gluon, it receives the color charge and changes accordingly. The gluon, in other words, is not just a messenger that transmits force. It is a messenger that actively changes the color states of the particles it connects. This means that gluons carry color charge themselves. They are not neutral intermediaries, but active participants in the color charge structure of the system. And this has a remarkable consequence. Gluons can interact with each other, not just with quarks, but among themselves. Photons do not do this. Two photons, passing through the same region of space, interact only very weakly and indirectly. In ordinary circumstances, the electromagnetic field is, to a good approximation, linear. Fields add without affecting each other. Gluon fields are different because gluons carry color charge. They are themselves sources of the strong force. They can exchange gluons with each other. This creates a highly nonlinear field, one in which the force between quarks does not diminish with distance in the simple way that electrical force does, but instead behaves in ways that are far more complex and, in some regimes, far more powerful. Think of it this way, though the analogy is imperfect, as all analogies at this level must be. In electromagnetism, field lines spread outward from a charged particle in all directions. They dilute with distance. Two charges, connected by electromagnetic field lines, experience a force that falls off as the square of the distance between them. In QCD, the field lines between quarks do not spread freely. They are pulled back together by the self-interaction of gluons. Instead of fanning out, the color field tends to form a narrow tube-like region of concentrated energy connecting the quarks, what physicists sometimes call a flux tube, and the energy in that tube remains roughly constant per unit length, which means that pulling quarks apart does not reduce the force between them. It increases the energy of the system. This is why quarks are confined. This is why you never find a free quark in nature, but we are moving ahead. Let us first dwell a little longer on the theory itself, on the remarkable framework that describes all of this. Quantum chromodynamics is the theory that describes the strong nuclear force at the most fundamental level, currently accessible to physics. It was developed during the early 1970s through the collaborative work of many physicists, Gell-Mann and others, at the level of quarks, with critical contributions from Harold Fritsch, Heinrich Leutwiler, David Politzer, David Gross, Frank Wilczek, and many more, and it has since proven to be one of the most precise and successful theories in all of science. The precision of QCD is worth pausing on. In physics, a theory is not considered successful simply because it explains things qualitatively. Explanation is the beginning of the work, not the end. A successful theory must make quantitative predictions, specific numbers that can be measured and compared with experiment, and QCD does this with extraordinary accuracy in many of its accessible regimes. But QCD is also a theory of considerable difficulty. Its equations are formally similar in structure to those of quantum electrodynamics, the theory of the electromagnetic force, but with an added layer of complexity that comes precisely from the self-interacting nature of gluons. In QED, calculations can often be performed as a series of increasingly small corrections, each step contributing less than the last. This method, called perturbation theory, works well when the coupling between particles is relatively weak. In QCD, the coupling between quarks and gluons is not always weak. At the energies accessible in many particle physics experiments, high-energy collisions, where quarks and gluons interact at very short distances, the coupling is small enough that perturbation theory works. This regime is called asymptotic freedom, a discovery for which Gross, Politzer, and Wilczek received the Nobel Prize in 2004. At short distances, quarks behave almost as if they were free particles, only weakly interacting. This allows precise calculations, but at longer distances, at the scales relevant to the interior of a proton, where confinement operates, the coupling becomes large. Perturbation theory breaks down the standard calculational tools of quantum field theory, become unwieldy or inapplicable. This is why some of the most important predictions of QCD, including the calculation of the proton's mass from first principles, required not analytical shortcuts, but enormous computational effort. Gluons are central to all of this. They're the particles through which the strong force acts, and their self-interactions are what make QCD so rich and so challenging. In quantum electrodynamics, the photon is neutral and does not interact with itself. The force law is relatively simple. In QCD, gluons carry color charge and can exchange gluons among themselves, creating complex feedback structures. In the field, this gluon self-coupling is encoded in the theory through the mathematical structure of the gauge group. For QCD, this is the group called SU3, which describes the symmetry of three colors. The gauge structure determines not only how quarks and gluons couple, but also how gluons couple to themselves. 3 gluon and 4 gluon vertices are predicted by the theory, interactions in which multiple gluons meet and exchange color charge directly without any quark involved. These gluon-gluon interactions are not hypothetical features of the theory added for aesthetic completeness. They are necessary consequences of the symmetry structure, and they play a crucial role in the behavior of the strong force. They are responsible, in particular, for the formation of those flux tubes that confine quarks, the concentrated ribbons of color field energy that keep quarks from separating. Another feature of QCD worth dwelling on is how it differs from electromagnetism in the way the force behaves at different scales. Electromagnetism becomes weaker with distance. Gravity becomes weaker with distance. The strong force, due to gluon self-coupling, does not simply become weaker with distance. In the regime relevant to confinement, it remains approximately constant as a function of distance, meaning that pulling 2 quarks apart requires a roughly constant additional energy per unit of additional distance. The total energy required grows without limit as the quarks separate. The quarks are permanently bound at very short distances and high energies. The coupling becomes small. The regime of asymptotic freedom at longer distances and lower energies, it becomes large. The regime of confinement. This is an unusual pattern, and it reflects the deep nonlinearity introduced by gluon self-interactions. quantum chromodynamics, is not a speculative theory. It has been tested extensively against a wide variety of experimental results, and it consistently matches what is observed. High-energy collisions at particle accelerators produce outcomes that are predicted by QCD with remarkable accuracy. The behavior of jets of particles, streams of secondary particles, produced when quarks and gluons scatter, matches QCD calculations. The structure of the proton, as measured in deep inelastic scattering experiments, matches QCD predictions. The existence and properties of bound quark systems, mesons, baryons, and others are explained by QCD. And yet, despite this success, there are aspects of QCD that remain computationally intractable by conventional means. The low-energy regime, the world of confinement and nuclear binding, requires tools beyond ordinary perturbation theory. If you want, I can also make this even more sleep meditation style, slower pacing plus breath pauses, which works extremely well for science narration videos. Let us spend some time with the idea of color charge, because it is one of those concepts in physics that rewards careful attention. Color charge is a property of quarks and gluons. It has three varieties, which physicists label red, green, and blue. Though these names are purely conventional, they carry no information about visual color or the electromagnetic spectrum. They are simply labels, borrowed from the additive primary colors, as a convenient analogy for why quark combinations form neutral composite particles. Every quark carries one of these three color charges. Every antiquark carries one of the corresponding anticolors. Antired, anti-green, anti-blue, and gluons carry combinations of color and anticolor charges, the rule that nature seems to enforce, a consequence of the dynamics of QCD, rather than something imposed from outside, is that all observable, stable particles must be color neutral. The technical term is color singlet. This means that no particle that can be isolated and measured carries a net color charge. Protons and neutrons satisfy this condition because each contains one quark of each color, one red, one green, one blue, and the combination of all three colors cancels to color neutral. In the analogy with visible light, mixing red, green, and blue light produces white light, which might be thought of as no color in an additive sense. In QCD, the combination of all three color charges produces a color-neutral state. There are other color-neutral configurations. A quark and its corresponding antiquark, carrying color and anticolor, also combine to a color-neutral state. This is the composition of mesons, the particles in Yukawa's original model of nuclear force. Pions, kaons, and other mesons are quark-antiquark pairs, bound by the strong force, their color charges canceling. Gluons, as mentioned, carry a color charge and an anticolor charge. There are 8 distinct types of gluons, corresponding to 8 independent combinations of color and anticolor. In the mathematical structure of SU3, the specific number 8 is determined by the mathematics. The symmetry group of 3 colors has 8 generators, and each generator corresponds to a type of gluon. This is not an empirical count, but a prediction of the theory, confirmed by the behavior of the strong force. In experiments, because gluons carry color charge, and because the strong force only allows color-neutral observable states, free gluons cannot be detected. In isolation, like quarks, they are confined. They exist only within the color-neutral environments of composite particles, or briefly within the quantum fields. Exchange between quarks. The exchange of color charge through gluons is the mechanism by which the strong force acts. When When a quark emits a gluon, the quark's color changes. When another quark absorbs that gluon, its color changes in a complementary way. Throughout this exchange, the overall color of the system, the combination of all quarks, remains neutral. The color charges circulate, passing from quark to quark via gluon exchange, but the composite system maintains its color-neutral character. This color circulation is, in a conceptual sense, the strong force at work. The quarks are pulled toward each other, not by any simple attractive charge, as in electromagnetism, where opposite charges attract, but by the requirement that the system maintain color neutrality. Through exchange, the gluons are the instruments of that exchange. They are constantly being emitted and absorbed, passing color from one quark to another, weaving the quarks together into a bound state that cannot unravel. There is something almost procedural about it, a constant bookkeeping of color charge, enforced by the structure of the theory, carried out moment by moment. Through gluon exchange, it is not a static bond, it is a dynamic equilibrium, an ongoing process, a quiet conversation in color that never stops, inside every proton. Right now, as you read or listen to these words, this conversation is happening. Quarks exchanging color, gluons carrying that color from one to another, the proton maintaining its integrity through the ceaseless activity of its interior. And this is true for every proton and neutron, in every atom, of every molecule that has ever existed. One of the most striking predictions of quantum chromodynamics, and one of the most thoroughly confirmed by experiment, is that quarks can never exist in isolation. They are always found inside composite particles, protons, neutrons, mesons, and other combinations. No free quark has ever been detected despite decades of sensitive searches. This property is called quark confinement. To understand why it happens, it helps to think about what the strong force does to space. In electromagnetism, when you separate two electrically opposite charges, the force between them weakens. The field lines spread outward in all directions. The force falls off as the square of the distance. Eventually, the charges are so far apart that they interact only negligibly, and each becomes effectively free. In QCD, the self-coupling of gluons changes this picture dramatically. When two color-charged particles begin to separate, the gluon field between them does not fan outward freely. The gluons themselves interact with each other, pulling the field back together. The result is that the color-electric field lines between the quarks are squeezed into a narrow tube, a flux tube or color string, rather than spreading in all directions. The energy contained in this flux tube grows with its length. The longer the tube, the more energy the system contains. To separate the quarks further requires adding energy continuously, not just a finite amount to overcome some potential barrier, but energy that continues to grow as long as the quarks continue to separate. At some point, an interesting thing happens. The energy contained in the flux tube becomes sufficient to create a new quark, antiquark pair from the quantum vacuum. Rather than the flux tube continuing to stretch indefinitely, it breaks. But when it breaks, the broken ends are capped by new quarks, a quark at one end and an antiquark at the other, so that two new color-neutral particles form from the remnants of the original system. This process repeats. Attempt to pull quarks apart, and new particles appear. Inject enough energy to force a separation, and you do not obtain free quarks. You obtain jets of new hadrons, new composite particles, each containing their own quarks bound by their own gluon fields. This is quark confinement, not a barrier in the ordinary sense, not a wall that quarks simply cannot pass through, but a dynamic process by which the field itself prevents isolation. The strong force does not weaken as the quarks separate. It maintains itself, and in maintaining itself, it continuously creates the conditions that prevent free quarks from existing. The experimental evidence for confinement is comprehensive. In all the decades of operation of particle accelerators around the world, In all the high-energy collisions that have been studied in detail, not a single isolated free quark has ever been detected. What are detected when quarks are struck with sufficient energy to begin separating are jets, collimated streams of hadrons produced by the fragmentation of the color flux as new quarks and antiquarks materialize from the injected energy. These jets are a signature of quark and gluon interactions. They are real, measurable, and they behave precisely as QCD predicts. Gluon emission, the radiation of a gluon from a struck quark, analogous to the radiation of a photon from an accelerated electron, produces its own jets, which have been observed and studied. The patterns of these jets, their energies, their angular distributions, all match the predictions of quantum chromodynamics. Confinement also explains the structure of the nuclear force at scales slightly larger than the proton itself, the force that holds protons and neutrons together in the nucleus. At these larger scales, the strong force between individual quarks inside different nucleons manifests as a residual force between the color-neutral nucleons. It is, in a sense, an echo of the stronger force within each nucleon, a leftover color interaction that leaks between protons and neutrons despite their overall color neutrality. This residual force is what Yukawa modeled with his pion exchange, and it is now understood as a consequence of the quark-gluon structure of matter and the dynamics of QCD. The exchange of pions between nucleons, Yukawa's original picture, is itself an effective description of this more fundamental process. Pions as quark-antiquark pairs can be exchanged between nucleons in a way that mediates an attractive force at nuclear distances. This works because the pion, despite being a composite particle, is light enough to be exchanged across the 10 superscript 1 meter distances of the nucleus without violating energy conservation in the quantum mechanical sense. But beneath the pion exchange lies the gluon exchange. The gluons are the true carriers of the force. The pion description is an approximate, emergent picture that is useful at nuclear scales. At shorter distances, inside the proton, only the full machinery of QCD and gluon exchange applies. We spoke briefly earlier about a remarkable fact, that most of the mass of a proton cannot be accounted for by the masses of its constituent quarks. The up quark has a mass of roughly 2 to 3 megaelectronvolts, and the down quark has a mass of roughly 4 to 5 megaelectronvolts. Tiny fractions of the proton's total mass of approximately 938 megaelectronvolts. If you simply added the quark masses, you would account for only about 1% of the proton's mass. Where does the rest come from? The answer lies in the gluon field, and in the kinetic energy of the quarks themselves as they move within that field. Both contribute significantly, but the gluon field energy, sometimes called glue energy, or simply the contribution of gluon self-interactions to the proton's mass, is the larger portion. This is a consequence of Albert Einstein's insight that energy and mass are equivalent, that mass is a form of energy, and energy carries mass. The formula E equals mc squared is perhaps the most famous equation in all of science. And in the context of the proton, it is doing something quite specific and concrete. The energy of the gluon field inside the proton contributes directly to the proton's inertia, its resistance to acceleration, which is what we measure when we measure mass. The proton, in other words, is not heavy because it contains heavy ingredients. Its quarks are light. It is heavy because its interior is filled with a highly energetic gluon field, and that field's energy contributes to the mass we measure. Current theoretical understanding, supported by numerical calculations in lattice QCD, a computational approach we will discuss shortly, indicates that the gluon energy contribution to the proton mass is substantial. Estimates suggest that gluon field energy and the kinetic energy of quarks together account for the overwhelming majority of the proton's mass, with the bare quark masses contributing only a small fraction. This is not merely an abstract theoretical point. It has direct consequences for the mass of matter in the universe. Protons and neutrons are the dominant constituents of ordinary matter. Their masses determine the masses of atomic nuclei, which in turn determine the masses of atoms, and everything built from them. When you stand on a scale and read your weight, the number you see reflects, ultimately, at the deepest level, the energy of gluon fields inside the protons and neutrons that constitute the atoms of your body. You are heavier than your quarks. The difference is gluons. This is, if anything, an invitation to re-examine what we mean by mass, not as an inherent property of matter in some simple pre-given sense, but as an emergent quantity arising from the dynamics of quantum fields. The Higgs mechanism, made famous by the discovery of the Higgs boson in 2012, gives mass to elementary particles like quarks and electrons. But the mass it provides to quarks is only that small fraction. The bulk of ordinary matter's mass arises not from the Higgs mechanism, but from QCD dynamics, from the energy of gluons and the kinetic energy of confined quarks. Two separate mechanisms give rise to mass in the standard model of particle physics. The Higgs field, which gives mass to fundamental particles like quarks and electrons, and QCD dynamics, which gives rise to the mass of composite particles like protons and neutrons through field energy and confinement. Both are necessary, both are real, and together they account for the mass of essentially all ordinary matter. The gluon field, then, is not simply a carrier of force. It is a reservoir of energy, an energetic interior environment that fills every proton and neutron in the universe. It is this energy that we encounter when we pick up a stone or feel the weight of our own bodies. The gluon field is, in a very concrete sense, part of why matter has weight. Since quarks and gluons cannot be seen directly, since they cannot be extracted from their composite particles and placed under a microscope, physicists must study them through indirect means. The primary tool for this indirect study is the particle accelerator, a machine that accelerates particles to very high energies and then allows them to collide, producing showers of new particles whose properties can be detected and measured. The logic of high-energy collisions rests on quantum mechanics and special relativity. When two particles collide with sufficient energy, that energy can materialize as mass, producing new particles that would not be present at lower energies. The higher the collision energy, the more kinds of particles can be produced, and the shorter the effective wavelengths at which the collision probes the structure of matter. This connection between energy and resolution, between how energetic the collision is and how small the features it can distinguish, comes from the wave nature of quantum particles. High energy corresponds to short wavelength, and short wavelength is necessary to resolve fine structure. To see inside a proton, to detect the quarks and gluons within it, requires collision energies sufficient to probe distances smaller than the proton itself. Deep inelastic scattering experiments, pioneered in the late 1960s at the Stanford Linear Accelerator Center, were among the first to reveal the internal structure of the proton. In these experiments, electrons were accelerated to high energies and directed at protons. When an electron collides with a proton at high energy, it can scatter not from the proton as a whole, but from a single constituent, a quark, inside the proton. By measuring the angles and energies of the scattered electrons, physicists could infer the structure of the proton's interior. The results were startling. The data indicated that protons contain point-like constituents, objects behaving like hard, distinct scattering centers within the proton. These were the quarks. The scattering patterns also revealed something about the quarks' properties, their spins, their charges, and the distribution of momentum among them. Crucially, the data also showed that quarks alone did not carry all the momentum inside the proton. In collisions at different energy scales, the fraction of momentum carried by quarks changed in ways that indicated the presence of other objects. Objects that carried momentum but had no electric charge, and therefore scattered electrons only indirectly. These neutral momentum carriers were identified as gluons. Their presence was inferred from the missing momentum that quarks alone could not account for. This is a characteristic mode of discovery in particle physics, inferring the existence and properties of unobservable particles from the behavior of observable ones. The gluon was not seen directly in these early experiments. Its presence was felt through its effects on the quarks, on the way quark momentum was distributed, on the way scattering patterns evolved with energy, on the way new particle production occurred in collisions. Later, at higher energy electron-positron colliders, a more direct demonstration of gluon effects became possible. When a quark and antiquark are produced in an electron-positron annihilation, they typically fly apart in opposite directions, producing two back-to-back jets of hadrons. But sometimes a third jet appears, a stream of particles at a different angle. This third jet is the signature of a gluon. When one of the quarks radiates a high-energy gluon before the two separate and fragment, that gluon itself produces its own jet. 3 jet events were first observed at the Petra accelerator in Hamburg in 1979, and were immediately recognized as evidence for the gluon's existence. This 3-jet observation was a milestone. It moved the gluon from a theoretical necessity to an observed phenomenon. The patterns of 3-jet events, the rates at which they occurred, the angular distributions, the energies of the jets, were consistent with predictions from quantum chromodynamics. The gluon was real. Modern particle colliders operate at far higher energies than those early machines, and can produce gluon effects in much greater detail. The Large Hadron Collider at CERN, which operates by colliding protons at energies of multiple teraelectron volts, produces collisions so energetic that individual quarks and gluons within the protons can scatter from each other, producing jets and secondary particles that are detected in enormous, highly instrumented apparatuses surrounding the collision point. Much of what physicists now know about the distribution of gluons inside protons, how many there are at a given energy scale, how their density varies with the energy of the collision, how their interactions contribute to the production of various particles, has been learned through careful analysis of data from these colliders, compared against the detailed predictions of QCD. The study of the proton's gluon content continues at dedicated facilities as well. The Electron-Ion Collider, currently under construction at Brookhaven National Laboratory in the United States, is designed specifically to measure the three-dimensional structure of the proton and nucleus, to map, with greater precision than ever before, the distribution of quarks and gluons, and their contributions to the proton's properties, including its spin. There was a time, a brief, extraordinary time, at the very beginning of the universe, when matter existed in a state we have never encountered in any ordinary circumstance, and only rarely and briefly recreated in the laboratory. A state in which quarks and gluons were not confined inside protons and neutrons, but moved freely through a hot, dense, seething plasma. Physicists call this state the quark-gluon plasma. According to current cosmological understanding, the universe in its earliest moments, in the first microseconds after the event that began its expansion, was filled with temperatures and densities so extreme that quarks could not bind together into composite particles. The energy per particle was so high that the strong force, despite its power, could not maintain confinement. Quarks and gluons moved more or less freely, interacting, but not forming stable, bound structures. In this state, the universe was not made of protons and neutrons. It was made of the ingredients of protons and neutrons, the quarks and gluons themselves, existing as an undifferentiated, incredibly hot and dense medium. Physicists believe this plasma filled the entire observable universe and was maintained at temperatures many orders of magnitude higher than anything in the present-day universe. As the universe expanded, it cooled. This cooling is a fundamental feature of the Big Bang theory. Expansion dilutes the energy density of the universe, and as energy density falls, temperature falls. And as temperature fell below a critical threshold, estimated to be on the order of 150 to 200 megaelectron volts, a temperature roughly equivalent to 2 trillion degrees Celsius, something happened. the quark-gluon plasma underwent a transition. Quarks began to combine. Gluons began to confine those quarks. Protons and neutrons formed from the freely moving quarks and gluons of the plasma. This transition, sometimes called the QCD phase transition or hadronization, occurred approximately 10 microseconds after the beginning of the universe. From that moment, the quarks were no longer free. They were bound into hadrons, protons and neutrons and their short-lived siblings, and have remained bound ever since. The universe transitioned from a world of free quarks and gluons into a world of composite particles. The protons and neutrons that would eventually form atomic nuclei combine with electrons to form atoms, condense into stars and galaxies, and, after billions of years of stellar evolution, provide the atoms from which planets and living things are made. The quark-gluon plasma is not merely a historical curiosity. It can be recreated briefly and in small volumes at particle colliders operating at sufficiently high energies. When gold nuclei or lead nuclei are accelerated to nearly the speed of light and collided head-on at facilities like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, the energy deposited in the collision region is sufficient to melt the protons and neutrons into a quark-gluon plasma for a very brief interval, on the order of 10 superscript 2 superscript 3 seconds. During that brief interval, the plasma expands and cools rapidly, and then hadronizes. The quarks and gluons recombine into protons and neutrons and other hadrons as the temperature drops below the critical threshold. The products of this hadronization are detected in the surrounding apparatus, and their patterns carry information about the properties of the plasma that briefly existed. Research at these facilities has revealed that the quark-gluon plasma is a remarkable substance. It is not a simple gas of freely streaming quarks and gluons, as was initially expected. Instead, it appears to behave more like a nearly perfect fluid, a liquid with extraordinarily low viscosity, one in which the quarks and gluons interact strongly even in the deconfined phase. Understanding the properties of the quark-gluon plasma, how it flows, how it thermalizes, how it hadronizes, is an active area of research connecting particle physics, nuclear physics, and even aspects of condensed matter physics. The early universe, in this sense, left a lasting imprint. The protons and neutrons that constitute ordinary matter today are the relics of that primordial plasma's cooling. The gluons now confined within those protons were once briefly roaming free through a hot, dense sea. That they are now bound, now weaving their invisible threads between quarks in the darkness of every nucleus, is a consequence of a transition that happened in the first 10 microseconds of cosmic time. We have touched on the idea that gluon field energy contributes to the mass of the proton. Let us now consider this more carefully, because it is one of the more profound and underappreciated results of modern particle physics. The proton has a mass of approximately 938 megaelectronvolts, expressed in the energy units that physicists prefer. The neutron is slightly heavier, at about 940 megaelectronvolts. These are the basic building blocks of atomic nuclei, and their masses determine the masses of essentially all ordinary matter. Now, as noted earlier, the bare masses of the up and down quarks, the quarks from which protons and neutrons are built, are only a few megaelectronvolts each. Adding the three quark masses gives something on the order of 10 to 15 megaelectronvolts, which is less than 2% of the proton's total mass. The remaining, approximately 98%, arises from the dynamics of QCD, from the kinetic energy of the quarks moving inside the proton, and, importantly, from the energy of the gluon field that confines them. This is mass arising from energy in the most literal sense, of Einstein's equivalence, the calculation of the proton mass from first principles, from the fundamental parameters of QCD, is one of the great achievements of modern computational physics. It requires a technique called lattice QCD, in which the equations of QCD are discretized onto a four-dimensional grid, 3 dimensions of space and 1 of time, and solved numerically using supercomputers. By working on a lattice, physicists can handle the non-perturbative regime of QCD, where ordinary perturbation theory fails. Lattice QCD calculations have successfully reproduced the proton mass to within a few percent, starting from nothing but the fundamental parameters of QCD, the coupling strength, and the quark masses. This is a remarkable achievement, confirming that QCD really does describe what is happening inside the proton, and that the mass of ordinary matter really does emerge from gluon field dynamics and quark motion. As the theory predicts, the broader implication is worth contemplating. The mass of the ordinary matter in the universe, the mass of every proton in every star, every neutron in every atomic nucleus, every atom in every planet and living organism, is overwhelmingly the product of gluon field energy and quark kinetic energy. Inside hadrons, the Higgs field contributes the elementary quark masses, without which matter would behave very differently. But the bulk of ordinary mass is a QCD phenomenon. In a sense, the strong force, mediated by gluons, is responsible for the fact that matter has the mass it does. Without the gluon field and its confinement dynamics, protons and neutrons would be negligibly light, and the chemistry, astrophysics, and biology that depend on matter having appreciable mass would be impossible. Stars could not form, nuclear reactions could not power them, life could not arise. This is not a mystical observation. It is a factual one, grounded in detailed calculations that match experimental measurement. The universe has the mass it does, in large part because of gluons, for all the success of quantum chromodynamics, and it has been a theory of remarkable success. There remain aspects of the strong force that are not yet fully understood. This is not a failure of the theory, but a reflection of the genuine difficulty of the problems it poses. The central challenge is computational. The equations of QCD are well established. They are not in dispute, but solving them in the regime of confinement at the scales relevant to nuclear binding, proton structure, and the mass of hadrons is extraordinarily difficult. By any known analytical method, the coupling constant of the strong force at these scales is not small, which means the standard technique of perturbation theory, expanding results as a series of small corrections, does not work. The alternative, lattice QCD, is powerful but demanding. By discretizing spacetime into a grid and solving QCD numerically, physicists can access the non-perturbative regime, but the calculations require immense computational resources. Each lattice calculation involves integrating over an enormous number of variables the gluon field values at each point on the lattice across many different field configurations using statistical sampling methods called Monte Carlo techniques. The hardware requirements for state-of-the-art lattice QCD calculations are substantial. They have driven the development of specialized computer architectures and have absorbed large allocations of time at some of the world's most powerful supercomputers. Progress has been steady but gradual as computational resources have grown. The precision and scope of lattice QCD calculations have improved correspondingly. Even so, there are aspects of QCD that remain out of reach for current methods. The structure of the proton, particularly its three-dimensional structure, including the spin contributions of quarks and gluons, is not yet fully understood. The proton spin puzzle, as it is sometimes called, emerged from experiments in the 1980s, showing that the spins of quarks account for only a fraction of the proton's total spin. Gluon spins and the orbital angular momenta of both quarks and gluons must also contribute. The precise apportionment of the proton's spin among these contributions is still an active area of research. The gluon contribution to the proton spin, sometimes called the gluon helicity, has been measured at particle colliders and found to be significant, but a complete and precise picture remains elusive, mapping the full three-dimensional distribution of gluons inside the proton, what physicists call the generalized parton distributions and transverse momentum distributions, requires experiments that have only recently become possible and others that are still being planned or built. There are also theoretical questions about gluons that remain open. The possibility of bound states of gluons alone, particles called glue balls, is predicted by QCD. If color-neutral combinations of gluons can be formed without quarks, they should exist as stable, or at least long-lived particles with characteristic masses and decay properties. Experiments have searched for glue balls for decades. Some candidate states have been identified, particles whose properties might be explained by a glue ball interpretation, but no definitive, unambiguous identification of a glue ball has yet been made. The difficulty lies partly in the fact that glue balls are expected to mix with ordinary quark-antiquark states, making them difficult to isolate. These open questions are not embarrassments for QCD. They are the natural frontier of a mature and precise theory, confronting questions that require methods, experimental and computational, still being developed. Science advances by identifying what it does not yet understand, and the open questions in QCD point toward real and tractable physical phenomena, waiting to be better characterized. The ongoing effort to understand gluons fully, their distribution inside hadrons, their contribution to spin and mass, the existence and properties of gluon-rich states, represents some of the richest ongoing work in particle and nuclear physics. There is something worth pausing on in the picture of matter that quantum chromodynamics and the study of gluons have given us. It is not dramatic. It does not lend itself to simple visual metaphors, but it is, in its own way, quietly extraordinary. Every atom around you is built around a nucleus. Every nucleus contains proton and neutron, and inside each of those, invisible to any microscope, inaccessible by any direct means, gluon are at work right now, constantly exchanging color charge between quarks, maintaining the bound state that defines each nucleon, carrying the energy that constitutes the bulk of ordinary matter's mass, not occasionally, not intermittently, continuously, without pause. without variation, without any response to the macroscopic events that seem so large and consequential from our perspective. You can hold a stone in your hand. You can feel its weight, its texture, its temperature. It seems solid and definite, a thing with clear edges and a fixed shape. But within that stone, at a scale more than 10 million times smaller than the width of a human hair, the quarks inside each proton and neutron are in constant motion, connected by gluons, exchanging color charge, in a dance that has not paused since those protons formed from the quark-gluon plasma more than 13 billion years ago. The stone is not still, it only appears still. At the deepest level we have so far been able to probe, it is a system of extraordinary activity, a quiet storm, invisible to all ordinary instruments, sustaining the structure of matter through the ceaseless action of the strong nuclear force. This is true of every material thing: the chair or floor beneath you, the air moving past you as you breathe, the water in your cells, the carbon in your molecules, the calcium in your bones. All of it, every atom, is held together at the nuclear level by gluons, and those gluons are never resting. The gluon's invisibility is not a deficiency of our instruments. It is a feature of its nature, built into the structure of QCD. Color confinement ensures that gluons can never be isolated, never detected in free flight. The way a photon from a lamp can strike your eye, they live and work entirely within the confined world of hadrons, in a scale of reality that is physically inaccessible to direct observation. And yet, what they build is everything we can observe: the stability of matter, the fact that atoms are not constantly disintegrating, depends on gluon confinement. The mass of matter, the fact that matter has weight and inertia, depends on gluon field energy. The nuclear reactions that power stars, the fusion that converts hydrogen into helium and releases the energy that sustains life on Earth, depend on the strong force mediated by gluons. The chemical elements, heavier than hydrogen, exist because gluons hold nuclei together against electromagnetic repulsion. Without gluons, protons could not exist. Without protons, atoms could not exist. Without atoms, none of the structure of the macroscopic world, not stars, not planets, not molecules, not life, could exist. The gluon is, in a very direct sense, foundational to everything, and it does its work invisibly, silently, without any detectable signature. At the scales we ordinarily inhabit, it is present everywhere and visible nowhere. It acts always and is seen never. There is something that invites contemplation in this, not mystical contemplation, but the kind of quiet reflection that science sometimes opens onto. When the full picture of a physical system comes into view, the universe appears, at its surface, to be a collection of things: rocks, water, air, stars, bodies, minds. But at the deepest level, currently accessible to physics, it is a collection of fields and their interactions. It is energy in constant exchange. It is structure maintained through perpetual process, and gluons are a central part of that perpetual process. The study of gluons is not finished. In many respects, it is in a phase of renewed energy and ambition, driven by advances in both experimental capability and computational power that are making new questions answerable. The electron-ion collider, planned for construction at Brookhaven National Laboratory in the United States, represents perhaps the most focused, near-term investment in understanding the gluon content of matter This facility is designed to collide electrons with protons and heavier nuclei at a range of energies, allowing precise measurements of the three-dimensional structure of the nucleon and nucleus. Among its primary scientific goals is a detailed mapping of gluon distributions, how gluon are arranged spatially inside the proton, how their density varies with the fraction of the proton's momentum they carry, and how their collective behavior changes when many nucleons are bundled together in a heavy nucleus. In heavy nuclei, gluons are thought to form a particularly dense state at certain energy scales, a regime called gluon saturation, or the color glass condensate. In the theoretical description, understanding how gluons behave collectively in this dense environment is important not only for nuclear physics, but also for understanding the initial conditions of heavy ion collisions and the properties of the quark gluon plasma. The continuation of heavy ion programs at CERN and Brookhaven will also contribute to the understanding of gluon dynamics in the deconfined phase. As detectors improve and collision energies increase, the properties of the quark gluon plasma, its viscosity, its thermal conductivity, the way it transitions to the hadronic phase, can be studied with increasing precision. These measurements constrain our understanding of quantum chromodynamics in the high-temperature regime and connect to the physics of the early universe. On the computational side, lattice QCD will continue to advance as computing resources grow. Machine learning techniques are beginning to be applied to lattice calculations, potentially accelerating some of the most computationally intensive steps. The goal of calculating the proton's full three-dimensional structure from first principles, including the gluon distributions, is within the horizon of the next generation of calculations. Theoretical work on QCD also continues, understanding the transition from the regime of asymptotic freedom, where quarks and gluons interact weakly and perturbative methods work, to the regime of color confinement, where they are strongly coupled, remains one of the deepest challenges. Connections between QCD and other areas of physics, including condensed matter physics and string theory, have yielded surprising insights. The calculation of the viscosity of the quark gluon plasma using string-theoretic methods, for example, produced a result remarkably close to what heavy ion experiments suggest. These unexpected connections hint that there is still much to learn about strongly coupled quantum field theories. The question of glue-ball bound states of pure gluon configurations remains open. Experiments at current and future colliders may produce definitive evidence for or against specific glue-ball candidates. Resolving this question would be a significant step in understanding the full spectrum of states that QCD allows. There is also the longer horizon question of whether QCD is itself a fundamental theory, or whether it is an effective description of some deeper structure. The standard model of particle physics, of which QCD is a component, is extraordinarily successful, but also incomplete. In certain respects, it does not include gravity. It does not explain the observed asymmetry between matter and antimatter in the universe. It does not account for dark matter or dark energy. Extensions of the standard model, grand unified theory, supersymmetry, and others make predictions that can, in principle, be tested at current or future colliders. Any discovery of physics beyond the standard model would almost certainly have implications for our understanding of the strong force and of gluons. The gluon is deeply embedded in the fabric of the current theory, and changes to the foundational structure would ripple through every sector of particle physics. For now, QCD and its gluons remain our best description of the strong nuclear force. The predictions of the theory match experiment with remarkable precision wherever the calculations can be performed. The questions that remain open are hard questions requiring new machines, new computational methods, new theoretical tools, but they are tractable questions, and the community working on them is productive. The story of the gluon is not complete, but the outline is clear, and it is already one of the more extraordinary things that scientific investigation has uncovered about the nature of reality. We have traveled a long way in thought, if not in distance. We began out here in the deep emptiness between galaxies, where the universe spreads its faint light across distances that exceed comprehension. We watched those galaxies drift unhurried through a darkness that has been accumulating since before there were stars to interrupt it. And then we descended, past stars and planets, past the visible surface of ordinary matter, past the level of molecules and atoms, into the nucleus, and then further into the proton itself, into that tiny, incredibly dense, perpetually active world, where quarks exchange gluons and gluons carry color charge. And the strong force keeps everything from dissolving into its fundamental constituents. Now let us ascend again slowly, back to the scale of ordinary things. You breathe. Each breath contains approximately 10 superscript 2 superscript 2 atoms. A number so large, it cannot be meaningfully visualized, only written down. Each atom has a nucleus. Each nucleus contains protons and neutrons. And inside each of those protons and neutrons, right now as you breathe and read and think, gluons are exchanging color charge between quarks, maintaining the bound states that make those particles what they are. In the bones of your hand, the calcium, the phosphorus, the carbon, gluons are at work. In the iron at the center of the Earth, still molten after billions of years of residual heat, gluons are at work. In the nuclear core of the Sun, where hydrogen fuses into helium, in the reactions that heat and light the inner solar system, gluons are central to the force that makes that fusion possible. In the light years of interstellar gas and dust that drift between the stars of the Milky Way, in every molecule of hydrogen, gluons hold quarks inside protons that have been stable since the first tenth of a millisecond of the universe. This is the scope of gluon activity. Not local, not occasional, everywhere, always in every proton and neutron that constitutes the matter of the universe. A silent, invisible process operating at a scale far below anything accessible to direct observation, sustaining the structure of matter with a quiet constancy that has never wavered since the universe cooled enough to allow confinement. We do not see gluons. We will not see them. No microscope in any conceivable future will resolve them as visible objects, because they are not visible objects in any ordinary sense. They are excitations of a quantum field, carriers of a force that operates on a scale incomparably smaller than light can probe. They are inferred from the behavior of the particles they affect, from the patterns of jets in collisions, from the success of quantum chromodynamics in predicting the properties of matter. And yet they are real as electrons, as real as photons. Their reality is confirmed not by direct sight, but by the extraordinary agreement between a theory built on their existence and the experimental results that theory predicts. Science does not always require that we see something to know it is there. Sometimes the most solid knowledge is inferred, built from indirect measurements and theoretical consistency, checked against experiment at every available angle. What is striking, in the end, is not the exoticism of gluons. It is their ordinariness, not ordinary in the sense of being familiar, but ordinary in the sense of being omnipresent, unremarkable in their constancy. They do not do anything unusual. They simply do what they do always without exception: mediate the color force between quarks, hold protons and neutrons together, contribute the bulk of ordinary mass, sustain the nuclear structure, on which all atomic chemistry depends. The universe appears at its surface to be made of solid things. Tables, mountains, bodies, planets. Things with weight and shape and clear edges. Things that resist being pushed through. But the appearance of solidity is the macroscopic result of physics happening at a scale we cannot perceive. At the scale of quarks and gluons, where nothing is simply solid, but everything is a dynamic field-based process sustained by the continuous exchange of particles carrying charge and momentum and energy. Matter is not still, it is a process, and gluons are part of that process. Not the whole of it, but a foundational part, a part without which the rest could not persist. There is a kind of patience in this that is characteristic of nature at its deepest levels. The universe does not hurry. The gluons inside every proton have been doing their work since the first moments after the Big Bang, and they will continue doing it, without interruption, without variation, without any apparent attention to the macroscopic events that seem so significant from our vantage point, for as long as protons exist. And protons, as far as current understanding indicates, are extraordinarily stable. The current experimental lower bound on the proton lifetime is enormous, far longer than the present age of the universe. If protons do eventually decay, it will be through processes beyond the standard model of particle physics, at timescales that dwarf the current age of the cosmos by many orders of magnitude. For all practical purposes, the gluons inside every proton in the universe will continue their work indefinitely. The quarks they bind will remain bound. The protons will remain protons. The atoms built on those protons will remain atoms. The matter of the universe, its stars and planets and clouds of gas, and here and there, the temporary but remarkable configurations of matter that call themselves living, will remain material. All of it resting on those invisible exchanges. All of it sustained by the constant conversation of color. All of it held together by the quiet work of particles that no eye has ever seen and no instrument has ever directly detected. The universe holds together, not by chance, not by mystery, but by force, by the strong nuclear force carried by gluons, described by a beautiful and precise theory, built through decades of careful observation and mathematical insight, by the work of physicists who asked what holds matter together and followed that question, step by careful step, into the interior of the proton and the mathematics of quantum fields. The answer they found is not simple. It cannot be made simple without losing what is most interesting about it, but it can be approached slowly with patience and care. And at the end of that approach, there is something that, if it does not satisfy in the way a completed puzzle satisfies, at least illuminates, casts a quiet light on the hidden architecture of the world. Gluons are that architecture's workers, silent, invisible, tireless, present everywhere, seen nowhere, carrying the force that holds matter together at its deepest accessible level, and in the space between stars inside every atom of every cloud of hydrogen drifting through the galaxy, within every proton that has ever existed or will exist. They continue their work, quietly, without pause, holding the universe together, fade to stillness,